All right. Looks like we're on time. Welcome, everyone. Sorry for the standing rows in the back. Hope you'll find it worthwhile to not spare your legs. So we're going to spend most of this hour chatting about experience of bridging two worlds. And I'm going to share some case studies. I'm going to ask some questions. By design, I sort of want a dialogue here, so feel free to engage, feel free to interrupt, ask questions. I do plan to not finish exactly on time, so I have plenty of time for Q&A and interaction. But even if we don't have enough time, or maybe some of you don't want to be on record here, do find me after the session, find me on the hallways. I'll be here till tomorrow morning. So don't be shy, reach out. I'm very interested in sharing experience here. So I very much look forward not to prescribe or tell, but to learn as well. So do come up to me, share your experience, if you have different opinions and so on. Also, I've been told to stay kind of close to the podium because the room has a weird shape. So I'll try not to move. If I go too far, just remind me, like, hide behind the podium. All right. So these are some of the places where I've done some damage in the past or currently. If they look familiar, I'm sorry. And because I didn't want to disappoint, sorry, Robert. Couldn't help myself. So, Robert, how many of you have been in Robert's session yesterday? Oh, excellent. That's more than half of the room. Excellent. Good. So I think that's a perfect segue into what I'm going to talk about today. It's not like we're taking opposite points of view or anything like that. I very much see this as a continuation of the discussion we had yesterday, and I think we had pretty nice dialogue, nice questions. So this is very much a continuation, and I'm going to try and hope to succeed to answer some of those questions that Robert had on the slides yesterday. For the people on recording or who weren't yesterday in the room, I strongly encourage to find the video recording and watch it. All right, so disclaimer. I'm not here to convert anyone to Rust. Don't want to start any language wars. I'm not going to talk about syntax or bike shed various design decisions in the language. I'm not going to try to compare programming languages. I'm not going to try to sell you onto anything. I'm not going to sell you any library, any design philosophy. I'm not going to tell you to rewrite your stuff in Rust. That's for sure. And I think the main point here is that, and we've seen this yesterday in Robert's talk as well. The idea is that we need to learn to coexist. This is not a zero-sum game. For us to succeed, C++ and C don't have to fail. And for a very long time, we're going to have to learn how to build stuff where Rust and C coexist. And I'm going to spend a significant part of today's presentation talking about ways to improve and harden C and C++ code, and ways in which we can successfully bridge these worlds, and how we can develop software products in these hybrid environments, hybrid projects, and how we can manage these transitions. I'm going to share some case studies from Microsoft and from other companies as well. I'm going to intentionally not use the remote so I don't go away. OK, so this talk is not about programming per se. I don't even think I have a snippet of code. So if that's what you're looking for, please make room for the standing people. So it's not about left and right, compare, transform your code, that kind of thing. It's more about engineering. not programming per se. It's about how we evolve the systems, the challenges we face when we set out to do these ports, when we want to write new components in Rust, when we want to port existing stuff to Rust, how we interop, and challenges along the way. By the way, for the people who don't know the Flamingo book, there's a link right there. And also, as a worthwhile mention, all my slides have lots of links in them. So when you do get the slides, afterwards, if you're curious, just click around. Plenty of links. All right. So I'm going to talk about challenges of bootstrapping a new team, bootstrapping a project, finding the right combination of skills in terms of systems experience, programming, Rust experience, service development experience, and so on. And challenges of onboarding new people and hiring and all sorts of interesting things. And I'm very much interested to hear stuff from your companies, from your projects, if you can share. So I'm trying to sort of set some expectations, tell you about some misconceptions that we've seen, and maybe tackle some occasional myths around these things. So rough path towards these things is why would teams want to be interested in Rust? Some of the challenges on the path to Rust in terms of learning, bootstrapping, engineering systems, that's a big deal. So again, going back to the thing that it's not just about writing the Rust code. Engineering systems is a big part of the equation. Of course, interop, not living in isolation bubbles. Rarely you will find situations where you have perfectly isolated systems that you can not interact with outside things. And all sorts of problems, and some wins. All right, but first, why are we interested in these kinds of things? Because it's not like we're just bored and, oh, let's learn a new thing and let's put everything upside down and figure out how to deal with it. There are reasons. And I would say the reasons mainly fall into three categories, I would say. First one would be security vulnerabilities, stuff that goes kaboom, and you need to deal with that. And they're costly. And you want to reduce these incidents. You want to have quick ways of mitigating them, and try to eliminate as many of these headaches as you can, right? Then there's the, let's call it, I don't know, government scare, institutions that come up with various things to push us over the edge. All sorts of regulations, all sorts of mandates, all sorts of prescribed things to lock us down or to push us to improve, however you want to see it, and security initiatives, right? We've talked about these for a couple of years now. And the third one, maybe less obvious to everyone, is cutting down costs. And I want to stress here because maybe for this audience, primarily interest in Rust or Rusty things mainly comes from C, C++, systems programming, universe, pursuing or being interested in Rusty things. But there's a different audience, and that is people who are doing service development, writing microservices in whatever language. For Microsoft case, it's mostly C# and .NET. And there's a substantial class of projects and people interested in that audience in Rust, not for the security benefits or getting rid of some government agency, because those systems are by far and large secure, but for costs, because they see Rust as a cost-saving opportunity in reducing operating costs in data centers. Okay, so I think we've established that C++ is inherently unsafe, and there's not much we can do about it. notice the asterisk there. I have lots to say about the asterisk. But we've known this for many, many years. Again, from Microsoft point of view, again, very skewed point of view, but the one I care about, CVEs, and I would say memory vulnerability and memory safety issues are still the dominant cause of CVEs in Microsoft. Roughly, they've always been between 60, 70 something % of all CVEs. And if you want to see like a more detailed breakdown, I don't know if that's quite readable. You have heap corruption, heap out of bounds reads, stack corruption, type confusion, uninitialized stuff, and use after free. Roughly the breakdown. Sorry if the font is too small for the people in the back. All right, so let's think about some of these classes in how we evaluate them with regards to the systems languages that we use at Microsoft. So we have object lifetime, type safety, bound safety, and uninitialized safety, sort of picking the most obvious contenders here. So I'm not going to try to go through all the rows, columns in the table here. I'm just going to leave them a bit for you to glance. We can sort of see the appeal of the Rust promise in terms of checking these boxes more readily than we can for C and C++. That doesn't mean we can't check some of these boxes for C and C++, but we need extra effort, extra tools, extra pain. And for some of those, it's impossible to prove and improve the situation significantly. So in terms of, if we go further down into bug classes and potential mitigations, there's a couple of them that have deterministic or probabilistic mitigations. And again, you can safely ignore the percentages there. I just took the data from internal presentation, but we can mostly solve some of these for C++ with extra tuning and better code gen. But there's some of them that are inherently impossible to get any confidence about. We can say that we can tick a box and we did the best effort, but we can't get any significant confidence that we address those issues. And statistically, we see improvements. So when we deploy these hardening techniques, these extra gates to make sure that we improve the security of this native code that we ship, we see statistical improvements. But the improvements are not significant or proportional to the efforts involved in getting there. So some of the ongoing efforts, making step changes in our SDL operations to make further investments to meet the needs of our services, and new stuff that's coming up. Completing deployment of CodeQL to make sure we gain more quality control and more gates in our CI. And of course, we feed back learnings from operating these things at scale. So we actually do a lot of learning by just looking at huge amounts of data in the wild. We continue to invest in hardening C and C++ code. Like I was saying, it would be foolish to say, oh, this is a lost game, let's write everything in Rust, problems will be automatically solved. We are working and investing a lot in hardening existing C and C++ code, because it's a lot of code. But at the same time, we are standardizing on Rust and other memory-safe languages where we can. So we diligently choose where we invest in either ports or writing new stuff in Rust. Of course, we want to support the whole ecosystem, so we do contribute to the Rust Foundation. We do build developer tools, and we started heavily investing in developer tooling for Rust so that we help the lives of internal developers who are on this journey and in the community at large. So we're attacking these problems, I would say, on multiple fronts. We're improving the situation of existing stuff, and we're creating these bridges and starting rolling out better and better tooling and libraries to help these projects that are seeking refuge under Rust. Again, I'm going to spend some time now on improving the situation for C++ and C. So C++ will never be 100% safe language. Let's get that out of the way right now. When I say safe, I mean all these kinds of safeties. There's many types of safety, not just the ones that I showed in those stats and charts. But it can be much, much safer with proper tooling and some discipline. So short term, we're investing in tactical efforts to eliminate the attack surfaces as much as possible, or reduce them. We try to block classes of exploit techniques by smart tooling or code gen. We do a lot of static analysis for potential vulnerabilities, so try to proactively find these things, and of course, lots of dynamic analysis and fuzzing. And we've deployed over the years, last 20 or so years, lots of tools and compilers, things and components and other binary stuff, post-compilation and all sorts of acronym soups that some of them I don't even know what they mean. They all do their part to improve the situation. Long term, there's more strategic investment going on our side in a sort of a combination of software and hardware mitigations to detect and eliminate these safety issues, memory safety issues. Things like guaranteed initializations, pool zeroing, cast guards, memory tagging architectures, which can have a bigger, broader impact long term. But these are significant efforts that are not immediately rolling out. For example, one strategic one on memory tagging would be to help developers catch these bugs, signal stuff like hardware, with support for hardware address sanitizer, to be able to find these things and prevent them to being shipped to customers or being exploitable if they are shipped. So there's a non-trivial CPU, a memory overhead here, but it's good enough in some scenarios to be enabled by default in production. And I would say those being good enough for these most of these scenarios I would say is a good indicator that people will actually turn it on. Google to deploy this to Android soon. Apple is expected to deploy these kinds of things in their devices as well. And we are working with silicon partners in designing these kinds of memory tagging architectures that scale a vast range, from the smallest things to our big Azure servers. And the goal is to, by default, make this an on path in Windows that we're gonna sort of not opt in into security, but rather have it on by default. And of course, the plan is to secure the cloud as well, right? All right, so we've seen a lot of, I think for the past 3 years, a lot of talks on all sorts of takes and responses to security and these mandates that we have to deal with somehow, ranging from acknowledging the issue, identifying common pain points, identifying potential solutions and strategies and good practices, talking about undefined behavior and unbounded undefined behavior and so on. So it's not exactly a new thing here. Just highlighted a couple of talks that I liked on this topic. I need to address UB because people tend to obsess just about memory safety, but sort of forget the elephant in the room here. So I wouldn't say C++ can be totally safe until we could get rid of all of UB. And this is unrealistic. We can't eliminate all UB in the language for good reasons. But at a minimum, unbounded undefined behaviors should be eliminated. So we will never be able to make guarantees about safety of C++, but we can improve the situation significantly, including on the UB space. So, but when doing these kinds of things, we're always going to be faced with trade-offs. And I would say for tool developers, there's trade-offs to be made between performance, compatibility, all sorts of ABI guarantees, and for users as well, users of the languages and libraries and tools, because as soon as you have these under switches, either on by default or not, people are going to mess with the switches because they're there. And I would say that there's a bigger shift here that needs to happen, not just being there in terms of language design, library design, better tooling, better code gen, and so on, but also sort of in terms of priorities for projects and a mind shift for the people driving those projects. So it's a long journey, but we'll have to do it. Anecdotally or not, I do encourage you to read this blog post by Corentin Jabot on safety. It touches a couple of these issues. I would say it's a very well-written piece, funny and insightful. So if you're interested in sort of exploring some of these topics, give it a read. I think the full link is right there. You can even do it now if you're bored. It's much funnier. Anyway, so on lifetime safety, there's multiple approaches that have been around for years now. From garbage collection to dynamic memory analysis, statically enforcing all sorts of rules, either by the compiler or the language. We'd have opinionated things here, like the borrow checker in Rust, or the Circle experimental compiler that tries to bring this borrow checker philosophy to C++. But again, my claim is that that's no longer C++. So, but if you're curious, I strongly encourage you to actually check that out to find out what can be done with these kinds of designs in C++. Maybe C+++, I don't know. Anyway, so mutable value semantics, another strategy to address some of these things. Of course, no direct mutation, all these pure functional languages. Less so with traction in industry. And tooling, of course. Things like Clanked ID, MSVC, all sorts of commercial analyzers out there that can find all sorts of interesting things. From good stuff through false positives and making you work through piles and piles of things and configurations, but they're all helping. I'm not saying they're a breeze to use, and some of them are not even cheap, but are definitely worth it. So I would say it's worth spending time figuring out how they work, how to properly configure them, mine through the big pile of output from them, and figure out what you can fix, what you can address, and what you need to maybe suppress or temporarily defer. Definitely worth it. I would even go as far as saying you need more than one, because they each have their strengths and weaknesses. So overlap might be best. So give them a try. And of course, one of the cornerstones of the Rust design philosophy in terms of type system, that is how we deal with references and aliasing. Either multiple immutable references to the same piece of data, or a unique mutable a reference to that thing. Not any other combination. So I'd say when it comes to C++ and existing code, we need to shift from that always auto bullshit to almost always analyze. So we need to build this habit of job is not done when the stuff compiles. Job is done when we did proper analysis, when we did fuzzing, when we enabled all the possible gates we could in our CI pipelines to make sure that we have more confidence in the stuff that we're going to ship. So we need to get out of this mindset that we're done because it compiles. It's not enough. Even if we have, even in compilers, many interesting new switches and functionalities to harden the code. So there's all sorts of security technologies. I've copied some of these acronym soups here. We've had some of these for years with successful usage in projects. Just want to raise awareness. If you're not familiar with these kinds of acronyms, get familiar with them. And most of this stuff is not MSVC specific. They're available in all major compilers. Similar stuff. New thing, how many people have heard of these custom attributes? I literally see one hand, just one hand. Okay, I'm so happy I put this slide in. Okay, so do check them out. These are relatively new developments, let's say year maybe, if I remember correctly. I pasted some links there, again for your investigation pleasure. So these are lifetime annotations that you can use now in C++. No need for any fancy new compiler. They work now. So for situations where control flow analysis and regular tool inference cannot prove more or cannot help more, you can actually help the tools. You can explicitly decorate and express your intent with regards to how references and lifetimes are bound. It's not Rust lifetime annotations, but you can express intent. You can be more deliberate, and you can help tooling pinpoint real issues and not just flood you with false positives. I do recommend this presentation from last year's CPPCon. By far one of my favorite presentations from last year's edition, not just because I'm friends with Gabor, but highly encourage you to watch this. He goes into a lot of detail about current landscape, availability, how these kinds of things work, not just in MSVC. So strongly encourage you to check out this talk if you haven't seen it. My experience is that very few people are aware of it, but the people who have seen it say it's life-changing. Lifetime-changing, sorry. Okay, so I ranted a lot. C++ will never offer any safety guarantees, but we can definitely do a better job of securing it, right, with good tooling and a change in mindset, I would say. So this tweet was pretty popular exactly 2 years ago, right? Just rewrite everything in Rust. Rust is the future, blah, blah, blah. When a guy at this level usually says something like this, it has consequences, right? He's a pretty important guy in Microsoft. And when he says stuff like this, usually it doesn't end up with some likes and shares on Twitter. It ends up with stuff getting done. And stuff has been done. All right, so I have to acknowledge the cloud because that's sort of central to many things now. So there's this Azure Security Evolution, secure multi-tenancy, confidential compute, and Rust. So there's this whole mantra in Azure and in Microsoft in general of trust, build up trust in systems, in services, in products, and so on. So they like to play with this thing. But it's not just Microsoft. I think it's no longer news. By now, most people know that Rust is in the Linux kernel with Linus's blessing. So lots of things have been moving in that space. Lots of new developments. But there's some friction. Probably some of you heard some of the recent drama with the file system group in the Linux kernel, and people not being extremely civilized and sort of going beyond technical arguments. Again, communities and various interests and agendas sometimes conflict with technical priorities. But things are moving. So Rust in Linux is slowly growing. Of course, Rust is in the Windows kernel. There's been so since more than a year ago, right? In various stages and experiments. And I'm going to talk about some of these things. And of course, Rust is in Android as well and growing. Last stats I've seen, I think we're Android 13 and 14, so it's slowly growing in Android, significantly so. So I'm going to share some stuff now. Some of these case studies that have been made public, but there's more that I'm probably going to be able to talk about maybe next year. So there's more going on. But I'm going to share sort of a few case studies and tidbits from Microsoft. So in Windows 11, we ported two candidate components to Rust. And these are Direct Write and GDI. So I'll give you some context here. The idea is we didn't pick just random components and say, let's do this in Rust and see how it goes. So we can brag about it. We picked some strategic components, either because of their attack surface or vulnerability history, or about feasibility of onboarding on such projects and learning from them. Because we can't just pick any component that might be too difficult to onboard to Rust, either because of dependencies of how it's architected and so on. So when we choose these things, we consider many criteria about how we pick them. So we go through these steps of exploration, flighting, and production with them. And direct impact when we're writing some of these components from C and C++ into Rust is, of course, to improve security. But I would say an equally important thing as we begin this journey, and begin doesn't mean we did it this year, begin in terms of Microsoft 50-year scale, right? Is to gain experience. So I would say this is an equally important thing, to gain experience in transitioning these components in production to Rust, not just some hobby new project that nobody's using. So when we're evaluating for many of these new projects, we're evaluating many aspects here. The cost of learning, the cost of onboarding the new team to a new technology, the cost of engineering systems retooling, the cost of porting itself, how expensive it is to extend new stuff, not just port existing stuff, how ready are we internally to build, test, deploy, verify these things. So there's, again, going back to one of my very first slides, it's way more than just rewriting it to Rust. Sometimes that's the easiest part, not always. sometimes that's the easiest part. The hardest part is the engineering behind it. What it takes to, to get that new code and get it through all the engineering systems requirements in Microsoft to be able to test and ship that thing. It's not enough just to build it. So are we really ready in terms of tooling and pipelines and debugging and performance indicators and all sorts of other internal things that we need to check they still work? And what are the costs of maintaining these things long term? Because once you do the port, there's a significant cost of going forward, because the plan is not to create an alternative universe and abandon the old thing. The plan is how do we take this hybrid world now and evolve them together? How do we keep them working together? How do we make modifications in either parts, either the C++ part or the Rust thing? And the Rust thing continues to grow, to evolve, and so on. So how do we evolve these hybrid systems? And what's the cost of dealing with these hybrid systems? Are they really worth it? First such example that we tried in Windows is direct write component, and specifically direct write core. So if you're not familiar with this thing, is a stack for text analysis, rendering, glyphs, layout, everything related to putting text on screen in Windows. And direct write core is actually cross-platform, and that's the component that Office uses internally. So it's supposed to work on all platforms where Office runs. It includes Android, iOS, Linux, Windows, whatever. It's supposed to be everywhere. The direct write core. And we started with this port in 2020, and we ported this thing to Rust. And sort of to get an understanding of how we can carve this space with regards to this component. It doesn't live in isolation. It's not a bubble. We need to call out external stuff, and external stuff, of course, will call out into this component because it's a system component. Lots of apps are using it. And when you do these sort of targeted ports, you have to identify boundaries. And it's not always the final stage or the target boundary of your intended port or intended rewrite. Sometimes you have to carve out these boundaries in incremental fashion to say, okay, now first phase we're carving out this far, and we're doing it, and we want to make sure it works with everything else, and then we carve out more, until we sort of reach a natural stopping point for what we set out to do with that component, right? And in Windows, a lot of stuff is sort of COM-like, and even if it's not exactly like COM, because it needs to be cross-platform, some of these things work in COM ways. So they expose these kind of boundaries that are COM-like. So these turned out to be these perfect regions, these perfect targets that the team chose for these ports. So of course, Rust code is directly callable through these COM interfaces from outside. So because direct write exposes user level APIs, so they need to be able to call. And internally, it has dependencies. So we need to be able to bridge those gaps and have these natural boundaries actually work. I'm not expecting you to read this thing. Maybe when you get the slides, this is sort of like an infographic kind of thing, laying out the details of the project and various parts of it. I stole this from a colleague. So I'm more interested, again, going back to the engineering side of things. Again, this is not a big project. Direct write core is not a huge thing. Uh, so, and it was sort of a starter experiment for the Windows team. So very few experienced Rust developers and many unknowns, because none of these things were figured out, both in terms of the strategy to do that port and in terms of engineering systems. Roughly this sort of was the experience. So you can consider this first encounter experience kind of thing. What does it take to embark on some journey? Again, numbers may not have any meaning to you, but sort of maybe give you some clue that it's not in years investment. It can be done in a reasonable amount of time for a reasonable component, but not a trivial one. Another experiment that is a bit more involved is Win32 GDI. This is the component that handles graphic rendering, 2D graphic rendering. This drives all the Windows surfaces in Windows and so on. It's a very old component in the operating system from late 80s, early 90s. And it's perf critical. It was written mostly in C. It was targeting really old CPUs, highly optimized thing, of course used by everything in the graphical part of the operating system. So it's not a toy component, right? So lots of data types and APIs and many dependents on this component, of course. This was a challenging one, and it was specifically chosen because it's a challenging one. This has not been fully ported to Rust. It's a big thing. It's a big component. But parts of it are ported already, and more so. And we're validating this process. Windows does boot with the Rust version. All GDI tests pass again, but and the component is, of course, in flighting to prove viability in real-world scenarios, right? So, but it's a long journey. So this is a big component. Performance of the ported code was excellent. In some benchmarks, even better than the C and C++ version. I keep saying C and C++ version because I'm ashamed to say C++, because it's not really C++. But it's not really C. So anyway, C++. So performance is excellent, proven by Office tests, because this component, of course, is used in Office as well. Proven by micro benchmarks and so on. Again, as part of this learning and journey, we did notice shortcomings, and there were contributions to upstream Rust project with learnings from this experiment, things that we found out to be missing, and our teams contributed back. And we have team members actively contributing to the Rust project. So lots of calls to external C and C++ functions, still lots of unsafe code, of course, because this is a fairly large component, and just a tiny bit of it was written to Rust, the region handling code, and a bit more. And as we rewrite, so right now there's tons of unsafe in this bridge between Rust and the C++ parts of it. But as we rewrite more of it in Rust, this unsafe surface is reduced. So the more you migrate, the less unsafe surface you have in this boundary. Again, going back to these, carving out these regions of stuff that you can gradually, incrementally port. And of course, a big milestone here was being able to write a syscall in completely safe code. So again, this was a fairly significant learning opportunity. There's many more oxidation efforts going on in the company. Can't talk about many of them, definitely not on record, but I can sort of give you teasers if you reach out to me privately. lots of them, spanning from system components in Windows and other software that you know and use, to services that are running in Azure and services that are running in Substrate Cloud and other significant parts. Again, when we wanna, those service projects for Rust are mainly driven by either reducing latency or improving performance or reducing operating costs. Some myths around Rust onboarding. Many people, when they look at Rust, they sort of get scared because it has a very shouty syntax. A friend of mine likes to joke that I don't like Rust because it screams at me, it has exclamation points everywhere. So it is a sort of a learning curve. And the mainstream misconception is that it takes a long time to learn, to onboard, to become proficient in, and so on. This is a case study that Google published roughly 2 years ago around some of these misconceptions around learning, around quality of diagnostics, quality of generated code, challenges of interop and unsafe, and so on. I do encourage you to read it if you want. It's not exactly super new, so already 2 years old, but it gives you a glimpse of how these things go. Internally, we sort of saw the same kind of things. We saw that developers managed to onboard to Rust fairly quickly. It's not the kind of thing you become proficient in a week, right? It takes some time before you gain some confidence and become prolific at it. But it's not something that is a stopper. So we have yet to find people who say the friction on path to Rust is learning Rust or learning the libraries and ecosystem and so on. There's, like I told you, there's many other challenges related to engineering systems and engineering in general, how to build and evolve these systems in a hybrid way that are much more interesting and occupy a lot of our time rather than just learning the language and library. A couple of interesting blog posts. I'm trying not to, I'm intentionally pasting links from Google as well because they've been sharing a lot of this journey publicly, and I just don't want to make this all about Microsoft, right? So I intentionally put out some interesting articles that I liked from Google with regards to their Rust onboarding on various projects, including learning, onboarding, engineering systems, tools used, and so on. I do encourage you to read them. And even bare metal Rust, that's a big thing. I mentioned interop. So interop is increasingly becoming an important problem because the more stuff we're going to write, the more of these boundaries we're going to face in interacting with existing code. When you pick and choose and say, oh, I'm going to choose this tiny little component, I'm going to choose this nice little project because I know there's like a lower risk of hitting real problems interacting with dependents or dependencies. But when you get to a point where you need to go and do some serious stuff, then more of this interop will come up. And this is where we need to invest more in building these bridges. There's already pretty good tools out there. I linked a couple of them at the bottom of the slide. Crates and tools that can help bridging these gaps. Oh, and I forgot to mention the Windows crate. So if you're interested in interacting with Windows APIs, Windows crate is a must. But anyway, these are operating system agnostic tools to help you with Rust C++ interop. So let me be as frank as possible. The situation is not great right now. It's not bad either, but it's constantly improving. And the thing that is awesome is that big companies, because now they have vested interest in this succeeding, it's no longer an incubation project, it's no longer a hobby thing for some developers or some team in some corner of the company and so on. Big companies see this as a strategic move, and they're funding serious efforts to help this interop story. So that applies to many of your favorite big tech corporations out there. So they're investing seriously in there, and the interop situation is improving. It's not perfect right now, so I'm not gonna sell you any lies here. And you can do it, right? It's although the interop could be better right now, that's not a stopper. You can very well write hybrid C++ and Rust code and combine them in the same module and have them working. That's not the showstopper. It can be sometimes too loud, it can be maybe unnecessarily acrobatic or maybe too noisy, but that's not the showstopper. Again, going back, engineering systems and tooling, that's where the pain is and where we're working heavily to address that and improve it. So learning. I laughed so much when I saw this tweet. It's a fairly recent one, but I think it perfectly describes what I'm seeing in sort of friends and acquaintances being on this journey. So this is exactly the two kinds of reactions I'm usually getting from people I know. Anyway, so with regards to learning, there's plenty of books, materials, trainings out there, lots of good stuff. I would say the most successful thing, and again, Google is very open about this thing, and they published case studies about their internal success on this journey. Do read it. Don't believe what I'm saying here. They do have invested and built this internal curriculum that they're using with hundreds and hundreds of their engineers, and it's all open source or public. You can browse it. Has Rust fundamentals, basically all you need to know to get started and familiarize yourself with the concepts, plus specific verticals, stuff specific for Android, stuff specific for for Chromium development in Rust, stuff related to kernel development and embedded, and concurrency. So I found this resource very, very good, and all the people I've shared it with said they liked it and it served them well. All right, so now, again, going back to the code is not the problem. The sort of ecosystem and engineering systems around it is the problem. You have to consume some stuff. It's unrealistic that you're going to build everything from scratch. You will, in some way or another, consume some stuff that is done by others, right? And you need a way to not end up in NPM world. And when you get some transitive dependency on some weird ass crate that you didn't even know you were importing for some obscure reason, right? You don't want a pad left in Rust, right? So teams who started on this journey quickly discovered that just pulling in crates to solve the problem quickly is not a recipe for success. Sure, you can build a prototype, you can build your favorite hobby project and put it on GitHub. Tick mark, I'm a Rust developer. When you're building real stuff for production use, you need to pass some quality gates in terms of dependencies you're building on top of, right? In terms of, formally we call this software bill of materials or auditing, or in terms of, and there's many criteria to evaluate this stuff. So there's all sorts of considerations in terms of quality of the project you're building on, number of maintainers, health of container ecosystem, um, evolution over time. Is it viable? Is it maintained? Is it many criteria, many that you can evaluate. How many other tools are using it? Right? How many vulnerabilities are there in that project? Are there first time? If I want to upstream some changes, can I do that? Tons of things to consider when you're picking something to use, right? There's tools like Arbor that do these kinds of things, but it's pretty limited what it can do. I would say it's a good starter, but if you want to improve a more robust evaluation and dependency evaluation system, you need to go a bit further than this. But it's a very good start. I would start with this. Again, put in some links there, learn how to use it and how to integrate and so on. So again, we are taking a more in-depth approach here. How we look at the kinds of things we deem safe or good bet to build on in projects in the company. Sort of the evaluation system or rejection system, for example, criteria that automatically disqualifies certain crates, even popular ones, for being used internally for various reasons, right? So again, the list of things that we can investigate and evaluate on is not tiny. And of course, they have different sort of priorities in terms of how important they are in the scoring system. So we sort of build a scorecard based on these criteria, and some of them are more important than others. Again, it's not physics here. We came up with a system that we think it's good, and we're constantly adjusting it. So, but I would say you need to ask yourself the same kinds of questions. You might not use the same criteria that we're using, and by the way, we're not even publishing those things yet. But other companies are doing the same things. Other companies that are consuming open source Rust projects, they're using their own criteria, their own evaluation system. And my encouragement to you is to do the same. Build whatever things you deem worthy in terms of evaluating, and be diligent about it. Don't just pull something just because it's convenient. So there's risks when you're using these things. There's security risks, there's stability risks, maintenance related issues. So stability issues, you need to be aware that am I building on something that's going to be further developed? Can I upstream things into it and so on? Can I work with the core maintainers? Can I become a core maintainer on that thing and so on? You don't want to end up in a world where you just leech something and don't ask questions, or you just fork everything because you think you're smarter than community at large. That's not the successful strategy. So again, I strongly encourage you to invest in these things and try to build unified. I'd say it's important to be coherent here, because if each team builds their own criteria or their own system, it's not going to end up well, because at some point you will have to interact with some other components and so on. So even in big companies, you will end up having weird interactions and dependencies. So I would say strive for uniformity, like to invest in these engineering systems and make them automatable. So design the criteria scoring system, but automate it, so you can do these checks and you can actually query all these parameters, all these criteria can be queried programmatically from crates.io, from GitHub, all sorts of sources. So you can actually use tooling fairly easily to evaluate these things. You don't have to do this by hand. And you can easily vet any component that you want to pull into your project. Okay, so I would say the